Hi, I'm Noah van Delft, and as a communications manager, I'm standing here to introduce you to our progress update video of the Automotive Energy Challenge. As a group of 8 students, we were asked to dig into the specifications of a fully remote controlled electric car. It's about the size of an Audi R8. And I'm going to cover the following subjects. I'm going to give you an introduction to our project. We're going to cover the rolling resistance. We will be talking about the air resistance, about our dynamometer tests. We also have a programming part in our project, and we're going to give you a small conclusion. So it is our goal to race across the track with the least amount of energy consumption in the least amount of time. This way we will win our project and have the largest grade, so that's really our goal. To effectively do this, we developed an Arduino program. We are developing an Arduino program which will indicate when we have done exactly one lap using a toll payment system. And I will be programming a speed measurement system so that our driver knows when he's driving the correct speed. As a group, we've had to divide 5 tasks. Each physical test is done by 2 pupils, and the 2 Arduino programs will each be done by 1 person. We are going to determine wind tunnel, the air drag coefficient using wind tunnels, as you can see over here. Raphael and Robert will be covering this part. So for the past few weeks they have been doing research about the formulas regarding air drag, and they've been thinking of ways to do this the most effective way. By adding parts to the car and removing parts from the car. Then there's also the dynamometer test. These will be done by Stijn and Sanjay. As you can see, our car will be on a large spinning wheel and attached to a rope, so that we can determine the force and torque of the power on the road. Then there's the rolling resistance, which will be covered by Daan and Arnoud, and they will push the car up to a certain speed and then release it and then measure the average deceleration of the car, and this way they can effectively determine the rolling resistance. Then there's also the Arduino part, as I mentioned before. Walter will be covering the toll payment system, and I will be doing the speed measurement system. So the toll payment system has to do with an infrared sensor, and this way the car or the racetrack knows when the car is passing the toll booth. And I will be using LED bars. I will be using an RPM sensor, rounds per minute sensor, and this way we can measure the speed of the car and then express that speed in colors on our LED bars. To make sure we will finish this project in time, we have taken preliminary measures. Our first agreement would be to have a common agenda, a shared agenda. This way everybody knows what everybody has to do and when everybody's deadlines is. We also made personal deadlines, so that just kind of homework, so that everybody keeps track of the progress. The advantage of this is that we can talk to each other about whether we finished our deadlines or not, and also like push each other to really do it within the time. And the second measure we took is to have 2 weekly meetings. This way we can help each other out by giving each other feedback and by granting each other with ideas, so that everybody gets the most creative ideas to do our tests. we think by respecting these measures, we can avoid deadlines being missed and can avoid frustrations among our group members. So now Arnoud is going to tell you something about the rolling resistance. So I'll give the floor to him.
Yes, so we will be calculating the rolling resistance, and we'll do that by using a goes down experiment. That's basically pushing a car up to a certain speed and then letting it roll out to a complete standstill. There's a cogwheel mounted on the engine, on the motor, sorry. We will dismount that, so there won't be any friction caused by the electric motor. So we will only be using the friction of the tires in our calculations. There's a sensor placed above the magnet on the cogwheel. It measures the amount of pulses over time it generates. And one rotation of the cogwheel generates 2 pulses. That data then is transferred to the Arduino in the gray box in the car. That data then is translated to velocity and then stored on an SD card where it's logged into a CSV file. And we can access that CSV file for further use. Our test will be performed at Markthal in front of Metaforum. The reason for that is because it's the same place as the final energy challenge. So we will then be working with the same road surface and thus making our calculations very accurate. We will be pushing the car up to a certain speed with our hands. Then the RPM sensor will measure an increase in pulses over time, and then when the car is coasting down, it will measure a decrease in pulses over time. Then that data is sent to the Arduino. It's translated into a velocity over time diagram, then stored on the SD card where we access it, and then we will be calculating the deceleration. Of course, only of the coasting down part. To do this, we'll be using some equations. First, we'll be calculating the total resistance force with the vehicle's mass, which is around 12 kilograms, and the deceleration. Then, once we've calculated that, we'll be using this equation for the rolling resistance force. With again the total resistance and the gravitational resistance, but we will be setting that to 0 because we're not working with the slope. Also the air drag resistance we will neglect because we will be testing at very low speeds, so that won't do anything on the results. So basically our rolling resistance force is the same as our total resistance in our experiment. Then once we've done that, we'll be calculating for at the last the rolling resistance coefficient by using this equation with the rolling resistance force, the vehicle mass, and the gravitational acceleration. Our test will be performed multiple times and then take an average, the average result, and thus making it also more accurate. So now Raphael is going to tell you about the air drag resistance force.
Hello, I'm Raphael Ozo, and I'm together with Robert Rowan responsible for calculating the aerodynamic drag losses and finding ways to reduce those losses. First of all, I'm going to tell you something about the wind tunnel. After that, I'm going to tell you something about the testing setup. Furthermore, I'm going to tell you something about the equations you've used and the calculations we have done. Moreover, I'm going to tell you something about the testing procedure. And at last, I'm going to tell you something about finding the effective surface area. First of all, the wind tunnel. The wind tunnel is a closed circuit with an object mounted in that closed circuit. And and the air will be going past this object, and will be the speed of this air will be controlled by the fan and the electric motor. The testing setup. There's a small opening in the wind tunnel at the testing section. This makes sure that the pressure inside the wind tunnel is the same as the pressure outside. There's also a differential pressure meter. This differential pressure meter measures the pressure difference between the total air pressure and the static air pressure, and it is needed to eventually calculate the air speed. There's also a floating platform on which the car is sitting. This is actually needed to make sure that the car is not generating any rolling resistance. There's a force sensor attached to the floating platform, and this force sensor is actually measuring the aerodynamic drag force. Equations and calculations. First of all, we've got the equation for aerodynamic drag force. That is a half times rho times CD times A times V squared. Rho is the air density, A is the car's effective surface area, CD is the aerodynamic drag coefficient, and V is the velocity. To actually calculate the velocity, we've got another formula. That is the Bernoulli formula. It is PT is PS plus rho times V squared divided by 2. PT is the stagnation or total air pressure. PS is the static air pressure. Rho is again the air density, and V is the air speed. And after doing some rearranging, we came up with the following formula. V is the square root of 2 times the difference in P divided by rho. And we've got also another formula that's needed to calculate the aerodynamic drag power. It's PL is FL times V. PL is the aerodynamic drag power, FL is the aerodynamic drag force, and V is the velocity. At the testing procedure, we first did a baseline measurement. This measurement is needed to actually calculate the aerodynamic drag force of the floating platform itself. And we will be subtracting this value from all the other values we've measured when the car is actually sitting on the platform. And as you can see, we have got the whole scheme of the test we will conduct during the wind tunnel test. Finding the effective surface area, we first made a picture of the front of the car with a geo triangle in it, and after that we've cut away the picture except the car and the geo triangle, and we have measured how much pixels represent a certain amount of length in the geo triangle. And after that we will be calculating how much pixels represent the front of the car, and thereby we've measured the effective surface area in pixels, and with that we can easily calculate the effective surface area in square meters. Now Stijn is going to tell you something about the dynamometer.
Hi, I'm Stijn Houwers, and as part of our group's tank-to-wheel analysis, me and Sanjay are working on the dynamometer experiment. And today I want to update on our progress so far, and what still has to be done and what are we going to do. So we started off this by digging into what a dynamometer is and what we can do with it and how it works. And from this we started writing our test plan. In this test plan we have obviously provided some resources. We need our car, we need the dynamometer, and we need all the hardware and software that's needed to control both of these. The car and the dynamometer are both provided at the test location, same with the hardware and a big part of the software. A small part of the software we still have to provide, which is a road load profile. We have to program this in MATLAB. In this road load profile there are 3 vectors, one for distance, one for speed and one for force. We set both of these will be inserted into this program where we can set the force and set the speed and measure the actual speed and the actual force at the wheels. These 3 vectors I mentioned before, the distance and speed ones are pretty obvious. We are just setting some speeds between 0 and 50 km an hour because we think that's city driving, that represents city driving. And the distance is just to measure how long we are driving at such a speed so we can get time from distance and speed. And the force vector is somewhere between 12 and 20. At every speed we put in, we are measuring at a range of forces between 12 and 20. Because again, we think this is representative for city driving and for our car. This we have to provide at the test. The rest of all will be provided. So that's what we've done so far. Now we get to what we are going to do. And of course, from a test plan, we are going to perform these tests. We've actually split up the whole experiment in 3 separate tests with actually 2 sort of extra tests to get the most accurate result that we want. The first test is done to determine the rolling resistance of the roller and the car, because some power will be lost at the wheel of the contact point between the wheel and the roller. And we just want to know what power is lost between the battery and the wheels, so what's lost in the drivetrain. Therefore, we're also doing an extra experiment. This is test 3, in which the car will not be driving, the roller won't be turning, the wheels won't be turning, and the motor won't be turning. But the car will be switched on and some power will be lost from the battery. This is, for example, going to the Arduino or to the LED bars or other components in the car that are not part of the drivetrain. With these 2 figures known, we get to our second test. In this test, our road load profile is actually used. And we set all these different forces and different speeds. And from this, we know the torque at the wheel and we know the power at the wheel. During the running through this profile, we'll be measuring the current and the voltage at the battery, and with that we can calculate the power at the battery. So we know how much power is going into the drivetrain, we know how much power is coming out at the wheels, and we know how much is lost to other components and to the rolling resistance. And with that we can find what's actually lost within the drivetrain and not within other parts, and that's what we want. With this we can of course make efficiency, we can calculate the efficiency of the drivetrain and put it in such a graph as this one, with on the x-axis we put the speed of the car, on the y-axis the torque, and the colors represent in this graph the efficiency of the drivetrain. So the red part here in the middle is the most efficient part, so at these torques and at these speeds we will have the most efficient car, and this is what we're going to need. This graph is one of our deliverables. Same with that we actually know what the losses are and how much the losses are. So with all these results, what are we going to do with them? So as I said, we know what the losses are, we know what the efficiency is, and we need this for our tank-to-wheel analysis. We combine these figures with all the outcomes of the first experiment and the second experiment, and that will make our tank-to-wheel analysis, from which we can decide what point of the drivetrain and what point in our car, what speed is the most efficient, which we will then give to our programming guys so they can set it into their car, which Walter will now explain.
Yes, hello, my name is Walter and I'm going to tell you something about the Arduino part of the project. So I'm going to tell you something about our goal, about what we've done so far and what we still have to do. So the goals, first off we have the speedometer, which is going to let the driver know if he's driving efficiently or not. So what we're going to do is we're going to use the information from my colleagues, which have calculated the efficiency from a specific torque and speed, and we're going to translate that into a code which translates the speed, the correct speed at which the car is most efficient, and then it will have a visual aspect on the car, which in this case is the LEDs, turn on green or a other nice color. And as the toll booth, the goal is to let the toll know that the car has passed. So in this case, it has to receive an infrared signal, and it should send an infrared signal back so the toll booth knows, this car has passed. And so the signal also has to be our car specific, so it knows our car has passed. The progress so far, we identified the problem and figured out how to go to the solution. So basically that means we at first we didn't know really what to do because, well, there was a few information, but we dug deep in the canvas, and we found out the pin connection of the Arduino. So that means which components go on which pin. We can now upload a script to the car, so you have to connect it to your computer and then you can send it through the Arduino program. We saw the signal from the RPM meter on the oscilloscope. So, when the speed increases, the frequency increases as well from the signal. And we now know what the serial data input does. When we asked some people from the solder lab to help us with the speed sensor, they said, well, you should first figure out what this does, and now we know. So that helped us a lot as well. To be done still, we have to figure out what we have to code on the speed part of the project. So we have to think about how we can translate the specific frequency of the RPM sensor to a code which lights up the LEDs in a correct way. And for the toll booth, we still have to solder the infrared receiver and transmitter to the car. And we should know how to receive the signal from this specific frequency from the toll booth. And then we also have to make sure that the signal is sent the correct way via the transmitter in the correct frequency. So that was it for today. In an unlikely event, if you still have questions, please go to this email and email him or us. We will be sure to answer your question ASAP. So, thank you for listening.